So in fact, I was hoping to have a few more results. Basically, today I'm just going to present the main result and a few minor results and then some questions, and we're going to continue working on that. So the questions are really surprisingly basic in a sense. So in a sense, I'm quite surprised that people haven't thought of this before, or maybe somebody has, and somebody knows some of these answers. So we are just looking at this ideal, the Marczewski ideal, which was introduced in the 1930s approximately. The ideal S0 of all sets, all subsets of the Cantor space, such that any perfect set can be shrunk to a smaller perfect set, which is disjoint from A. So I guess many people have heard of this ideal somewhere. So this is a sigma ideal, not by definition, but because you can use fusion on perfect trees. This is not so hard. Borel sets in this ideal are exactly countable sets. This follows from the perfect set theorem. And actually, sex forcing is equivalent to Borel sets modulo this ideal. So there are some connections with sex forcing and with some other things. And we have the most straightforward variations. So we say that T in the Baire space is a Miller tree or a superperfect tree if every node in the tree has an extension which is infinitely branching. I suppose this is well known to many people as well. And by analogy, we define the Miller ideal to be all the subsets of the Baire space, such that a Miller tree can be shrunk to a smaller Miller tree disjoint from A. And by complete analogy, we can prove that this is a sigma ideal by using fusion. Borel sets in this ideal are exactly the sigma compact subsets of the Baire space, or equivalently those that are dominated by a function. And Miller forcing is equivalent. Miller forcing is the partial order of these trees. Is equivalent to the collection of Borel sets modulo this ideal. And finally, a Laver tree. It's a tree that has a stem, and beyond the stem, everything is infinitely branching. And the Laver ideal is defined analogously for Laver trees. And again, this is a sigma ideal. Borel sets coincide with the so-called non-strongly dominating ideal. It's a slight strengthening of the dominating family. It's not really relevant. And Laver forcing is equivalent to Borel sets modulo this ideal. Good. So these are fairly basic definitions. For example, there's this paper by Jörg Brende, Strolling Through Paradise, where he considers these ideals and a bunch of others and proves that they're all not containing one another and so on. So, okay, what do set theorists love to study? At least certain kinds of set theorists. Given the sigma ideal on the Baire counter space, you can define the additivity, covering, uniformity, and cofinality number. I suppose everybody knows these definitions. And it is pretty straightforward that these inequalities hold in ZFC. So arrow means less than or equal provable in ZFC. These are all trivial, assuming basic stuff about the ideal. The covering and the uniformity numbers are less than the continuum. This is also easy. And if I is Borel generated, then the cofinality is less than continuum, because there are only continuum many Borel sets. So in particular, for ideals that people have studied a lot, like meager, null, also this K sigma, and this other Borel generated ideals, these four cardinal invariants really lie between omega 1 and the continuum. So they're trivial in case of CH, and if CH fails, then they sort of measure how far, or what exactly happens between omega 1 and the continuum. Okay, and we are just looking at the Marczewski ideal, and this is the first thing that we can say, from which we see that this is slightly different than the Borel ideals that are typically considered. So the uniformity number, or the least size of a set which is not in the ideal, is in fact equal to the continuum. Why? Simply because take a set of size less than continuum, take a perfect tree, and partition it into continuum many perfect trees. This is very easy. One of them must be disjoint from A. Okay? So in particular, the cofinality must be at least the continuum. And it's a result which I suppose is a Volcker result, that actually the cofinality of the Marczewski ideal is above the continuum in Z of C, and this is the proof. We say that A is a disjoint maximal antichain in sex forcing if it's a maximal antichain, with the additional condition that two trees are completely disjoint. And it is well known and not too hard to construct disjoint maximal antichains in sex forcing of size continuum. How do you do this? Well, you have to start with some maximal antichain of size continuum, and then you can refine it simply by a straightforward induction using the following fact, that if we have one perfect tree which is incompatible to some initial segment of the antichain that we're constructing, then we can find a T prime which is actually a subset of T but completely avoids all the less than continuum many previously selected trees. Okay, this is just by the partition that we already saw before. So what we do, we fix such an antichain, and let me draw a picture. So we fix this completely disjoint antichain, T0, T1, etc. And we look at a potential base, so a continuum-sized collection of Marczewski null sets, and we simply pick, so this is x0, we just pick a point in T0 but not in x0, x1 we pick a point in T1 not in x1, etc. And the set that we pick, this y, will be not covered by any x alpha, however it will be small because it's a maximal antichain, so given any tree you can get inside one of those conditions, and then you find that there's just one point from the set, so you can shrink and avoid it. So this is a fairly simple argument. And now, yeah, okay, so I'll come back to this later, but the interesting thing is that even though the Marczewski ideal is just a classical ideal on the counter space, in fact the cofinality number is, unlike with the Borel ideals, it's actually strictly between the continuum and due to the continuum. So in some sense you could say that it behaves more like a cardinal invariant on the generalized bare space continuum to the continuum. So maybe there might be some connections, I'll come back to this later. There might be some connections with generalized bare spaces, which is a pretty fashionable field these days. Okay, so so then we were looking at these ideals, the Miller null and the Lever null ideal, and we were just thinking, what can we say about those? So, of course, we can prove that their uniformity is continuum by exactly the same argument, because given one of those trees, you can partition it into continuum many trees. So in particular, the cofinality is above the continuum. Now, if we can do this trick, if we can find a disjoint maximal antichain in Miller or in Lever forcing, then using the same argument, we can prove the cofinality is above the continuum. But recall what we did. How did we construct this object? Well, as I said, we used this idea that if a tree is incompatible to less than continuum many perfect trees, then we can find something. We can find T prime in T, but without disjoint from the initial segment. And essentially, what this is, you could formulate it this way: the additivity of the countable comma Marczewski null ideal. It means the least number of countable sets whose union is not Marczewski null. If you rearrange the quantifiers here, this is exactly the requirement. Which means that if we want to do an analogy for Miller and Lever, we need the additivity of this sigma ideal, the Miller ideal, to be continuum, and for Lever we need this non-strongly dominating ideal. And actually, this one is equal to D dominating number, that one equals B the bounding number, and therefore if D equals C, then the cofinality of the Miller ideal is C, and B equals C. And actually, So this proof works by disjoint antichains, but you can do a slight modification and you can strengthen the latter to this slightly stronger result. D equals to D, and the cofinality of the labor ideal is also So okay, this was somehow not so hard, but the following question still remained, and in particular, it was asked by Lipitsky in some private communication. The question is, okay, can we prove this in CFC? Can we prove that the cofinality of the Miller ideal and the labor ideal is above the continuum? And our main result is yes. So we proved that yes, in fact, they are above the continuum in ZFC. However, the proof does not actually use disjoint maximal antichains like this. So the following question, which I think is a very basic question, but somehow we don't know the answer, do disjoint maximal antichain of size continuum actually exist for Miller labor forcing in ZFC? So actually we have no idea. Okay, so I will talk a little bit about the proof. Might get somewhat technical. Oh, what happened?
You cannot.
I shouldn't do that. Oh, it's too smart. Okay.
You can use either one, but not the same. Not two.
Okay.
You can use it. You can just move it up.
And then.
But you can see this, right? Okay. So we consider. So for the proof, we consider trees instead of looking at the bare space and looking at trees from omega to omega, we consider trees from omega to 2 to the less than omega. And so how do these look? I mean, they're basically just, maybe you have some trees, let's say Miller tree, and that splits somewhere, and this things where it splits is actually going to be some collection of initial segments of rings in the counter space, something like that. Now, if given a function, fixing a function f in the counter space, let Tf be the tree of all strictly increasing initial segments of f. So what does that really mean? It means that if this is a sequence, and this is its last element, this is some s in 2 to the less than omega, then what we want is that the successors are exactly all the longer initial segments of f which extend s. So these special trees are a particular kind of Labor-Miller trees, and notice that given any branch through that tree, if we look at the union of the digits, we must obtain the function f. In particular, for different f and g, trees Tf and Tg are disjoint, therefore we have a disjoint antichain in Miller labor forcing, but it's not maximal. So the picture is really something like, if this is our space, omega to the omega, or actually it's 2 to the omega, then this is some very special antichain which occupies this very special part of the space. So we have this antichain here. And the main lemma is that given any Miller tree or any labor tree, either it must be compatible with one of those, or you can shrink it away. You can find a stronger S, which will actually have at most singleton intersection with every number. Right. So given some tree here, either you find yourself compatible with one of these conditions, or you're in a situation which is like this, and it has a singleton intersection, or maybe it's not. Okay, so just a few more words about this proof. Yeah, so how does this proof work? Suppose we start with an arbitrary tree. Again, in that space, first of all, we know that without loss of generality, we may assume that T contains only increasing sequences. So in other words, this arbitrary T that we start from must have some kind of shape like that. So it might not contain all of these successors, but it has to be the case that every extension, so that every time you take a sequence, the next digit is an extension in that sense of the preceding one. Why may we assume this? Because if that's not the case, if there's any part of the tree where this fails, then we just go sufficiently far, we find the place where it fails, and we are immediately disjoint from all of these. Because all of these trees do have that property. So if you just find one tree where it already fails, then all its branches will not have that property. So they'll all be destroyed. So it's a very easy situation. And now, assuming that T does have this property, we need this dichotomy. So we need to shrink it to an S such that either all branches through S actually converge to one F. This should say for one unique F. So either there exists an F such that all branches through S converge to that one, and that implies that S is a subset of TF, and therefore we are in this situation, in this compatibility situation, or we're in a situation where S is a tree where any two different branches must converge to different elements, and that will imply that it can have at most a singleton intersection with each tree. Now, okay, I was thinking that if I have time, I might sketch a few more things on the blackboard, but I guess I don't. So I'll skip the rest of the proof. It can get quite technical. Actually, for Miller coursing, it's not too hard. For labor, it gets very technical.
Some careful fusion from the other way.
Essentially, yeah, it's essentially a fusion. For labor, it's essentially a fusion as well, but it's much more technical. Okay, and why is this? Let's see why this is enough. Okay, so we're in this situation, right? And we want to prove, what do we want to prove? We want to prove that this implies that cofinality M0 is above the continuum. So again, we start with some collection of small sets, the potential base. We list S alpha, lists all the trees which are outside, essentially, except for a singleton. And then inductively, we again pick one point in each of these trees, but we do it in such a way that Y alpha is in T F alpha. We avoid X alpha, this is easy, but we also avoid less than continuum many of the S betas, which we can do because each one has only one element intersection. Okay, and we claim that this is a null set, which completes the proof. Why is that the case? Because let's take an arbitrary T, and by the main lemma, we can shrink it to an S such that either we are in one of those conditions and then there's at most one point in it, so we can shrink away from it. This is again easy. Or that's not the case, but then S is one of those S alphas. And then again, each S alpha has at most less than alpha many, so less than continuum many points, and again you can shrink it away from Y. So this is not a very difficult argument. The main difficulty is in this construction. Okay. So this is basically the proof. If anyone is interested, I can show you in more detail later. And now a few other things. So this is really going towards questions that we want to work on. We don't really have significant results. It's as I said before, the cofinality of these Marczewski ideals is really a cardinal invariant between the continuum and to the continuum. So could you maybe compare it to some other cardinal invariants in that space? And this is an observation of Rapitsky, that in fact all these cofinality numbers are larger than the dominating number in continuum with the continuum. So the second level, the higher level dominating number. Now this holds in ZFC because you're using the disjoint antichains, but for Miller and later, even though we proved our result, but apparently it doesn't help us to get this inequality in ZFC, so we only have it under this assumption. Okay, so this is sort of a lower bound. What about upper bound? There's a pretty stupid upper bound. I don't really want to go into that. So there's sort of an upper bound if you look at functions from the forcing to the forcing with the partial order of the forcing, but this is really pretty useless. And what can be done for the Marczewski ideals has been done by Yuda, Miller, and Cella in a paper from '92. So if we fix CH and we don't move that around, we just look at the next level continuum, we can, for example, make sure that the cofinality is exactly the second level continuum, which is any regular kappa. Moreover, we can also force that the cofinality number is less than the second level continuum. And by analogy, we can prove similar results for the Miller and the Laver ideal. But for example, what we don't know, it seems pretty basic, whether these numbers can actually consistently be different. And what we also don't know is whether they can be larger than the dominating number. Or it could just turn out that they're all equal to the dominating number and therefore equal to each other. So I think this is pretty interesting. I hope we have a solution at some point. Okay, well, I'm almost done, except that I wanted to mention how this can be generalized in a more abstract setting. So now we assume that, so instead of looking at Sexton, Miller, and Laver, we can make this kind of generalization. We look at the forcing partial order, assume that the conditions are trees, assume that it has this property that basically, given any tree, the intersection of the tree with a point condition is also in that forcing. We need B to satisfy some kind of fusion. We need B to be homogeneous. I'm going to explain what exactly it means. And we require that every tree can be partitioned into continuum trees. And then we can define the P0 ideal by analogy. And we can also look at the ideal, which is sigma generated by closed sets in this ideal. And if we do that, then we have a bunch of results along the line of things that we did in this particular case. So for example, covering of that ideal is a continuum, then we can prove that the cofinality is both a continuum. Also, if covering of meager is continuum, we can prove the same. If this additivity number is the continuum, then we can do that. I wanted to say this. So I want to say cofinality of P0 is larger than dominating number. This is always true. That's not what I want to say. And yeah, and assuming CH, we can extend. We can increase the cofinality number, and we can increase the second level continuum without increasing. But in general, we have no idea whether under certain assumptions you can prove, for example, that the cofinality number is about the continuum in ZFC. So here are all the interesting questions again. This is maybe the most interesting one. There exists disjoint maximal antichase size continuum in Miller and Laver forcing. I would be happy if somebody knows the answer. said, can we prove in set of C that the cofinality of these kinds of ideals about continue only before a reasonable class of B, or maybe there is a natural continuity. Then this question, can the cofinality numbers be different, and can the cofinality number convert into dominating numbers? So you see there's still plenty of questions, so I hope, yeah, I hope we work, and maybe we're successful with some of them. Okay, that's all. Thank you.
We have time for very short question because
You look at the dominating number of C to the C, but since sometimes the assumption is that D equals C, you might want to look at the dominating number of D to the C or D to the D or C to the D. I don't know, I'm just thinking, just looking at natural variance.
Yeah, but I'm not completely sure. Could be.
well, let's. We don't have time for more questions. Let's thank again the speaker. And we will proceed with this.